Okay, hi everyone, welcome back to this video on Cisco Packet Tracer, Chapter 7, Border Gateway Protocol, BGP. The internet is a huge network and is made up of many smaller networks. To learn about routes in other networks, each network has to run a routing protocol, while protocols such as EIGRP, Enhanced Interior Gateway Routing Protocol, OSPF, Open Shortest Path First, and RIP, Routing Information Protocol, work well for many networks. They do not scale to support the needs of a gigantic network like the internet, nor do they provide the level of administrative separation required. So BGP, Border Gateway Protocol, is used by ISP, Internet Service Provider, large enterprise to advertise IP routes to one another. In this chapter, we'll learn about BGP and its features when compared to other routing protocols. We'll also learn the commands used in BGP and configure it in Cisco Packet Tracer. What is BGP? BGP is a very robust routing protocol that is used to exchange routing information between multiple autonomous systems, AS. This brings up the question of what an AS is. An AS is a collection of IP prefixes, read IP networks that are maintained by a network operator. This network operator could be an enterprise or an ISP. Each AS has a number assigned to it called ASN, Autonomous System Number. Public AS numbers are assigned by the IANA, Internet Assigned Numbers Authority, to the RIPs, Regional Internet Registries. These RIPs in turn assign them to individual ISPs. Configuration of BGP largely depends on how an organization is connected to an ISP. There are four possible ways in which this can be done. A single homed, one link to one ISP. This is a simple design shown in the following screenshot and has one link for an enterprise connecting to the ISP. This design has no redundancy or failover. Dual homed, two or more links to an ISP. This design has a single ISP but has two or more links connecting it. This provides some amount of reliability in the event of link issues. The following screenshot has examples of dual homed design. Single multi-homed, one link to two or more ISPs. This case shown in the following screenshot has multiple ISPs with one link connecting to each of them. Dual homed, two or more links per ISP or two or more ISPs. This design shown in the following screenshot provides the highest level of reliability and availability. In this case, there are two or more ISPs with two or more links connecting each of them. BGP may not always be used in all previously discussed designs. For some designs, such as single homed, it is better to just have a static default route in the enterprise router towards the ISP and another on the ISP side for just the network prefix of the enterprise. However, implementing BGP on multi-homed networks ensures that the most efficient route is used, as these networks have two or more links to ISPs. There are two types of BGP: eBGP, external BGP, iBGP, internal BGP. External BGP. This type of BGP is used to exchange routes between two types of AS. The administrative distance of eBGP is 20. By default, the uptake packets in eBGP have a TTL set to 1 so that only directed connected BGP routers receive it. However, this behavior can be changed by using commands. Also, an eBGP peer will advertise all the valid routes it has learned from its eBGP and iBGP peers. When an eBGP neighbor advertises a route, it sets the next top field of the route to its own address, internal BGP. This type of BGP is used to exchange routes with an AS. The administrative distance of iBGP is 200. Updates in iBGP do not have TTL value limitations. An iBGP peer does not advertise a route to another iBGP peer if the route was learned via iBGP. This is done to prevent routing loops within an AS. The next top field of the route updates remains unchanged when one iBGP peer advertises to another iBGP peer. This behavior can be modified with the use of commands. BGP versus dynamic routing protocols. Even though BGP works like any other routing protocol, it differs from them a lot. IGPS interior gateway protocols such as RIP, OSPF, and EIGRP are enabled interface-wise. The network statement in the routing protocol configuration is used to mention network IP address, and all interfaces IP address that fall within the specific network range have a particular protocol enabled. On these enabled interfaces, these IGPs send out broadcast or multicast messages containing network route information. For this to work, two routers running IGPs have to be directly connected. The metrics used by IGPs to choose the best path are the number of hops, bandwidth, delay, and so on. On the other hand, BGP doesn't have the concept of interfaces because the entire router is considered to be in the AS. Its neighbors are not automatically discovered and have to be mentioned statically with the neighbor command. After this, BGP messages are unicast to TCP packets. BGP runs on TCP port 179 and listens to BGP messages. A neighbor doesn't have to be directly connected and can be several hops away, but by default, the TTL value of a BGP message is 1. So if a peer is not directly connected, it has to be increased. BGP's way of choosing the best path is entirely different from IGP's. It uses a variety of path attributes, PAs, such as next hop, reachability, weight, and AS path number of AS in the path to the destination. Moreover, BGP is designed for handling hundreds of thousands of IP routes, which consumes a lot of resources if done with an IGP. Configuring BGP in Packet Tracer. First, let's look at the command used in BGP. Router BGP ASN, for example, R1 config router BGP 120. This command enables BGP on a router and moves to the router configuration mode. The ASN can be any value between 1 and 65535. Once enabled, the BGP process must choose a router ID. By default, BGP uses the following methods priority-wise to pick a router ID. Configured. This is the router ID configured by using the BGP router ID router subcommand. Highest loopback. This is the highest numeric IP address configured on any up loopback interface at the time the BGP process is initiated. Highest other interfaces. This is the highest numeric IP address configured on any up non-loopback interface at the time the BGP process is initiated. A router ID can be explicitly configured using the following command: BGP router ID x.x.x.x. For example, we can use the following command to configure the router ID: route R1 configure router BGP router ID 1.1.1.1. For configuring a BGP neighbor, we can use the following command: R1 config router neighbor x.x.x.x remote ASN. For example, R1 config router neighbor 10.0.0.2 remote AS130. The ASN entered for remote as should be the ASN of the neighboring router. This changes in EGBP and is the same in IBGP. Let us look at an example. The following commands are used to change the EBGP. R1 config router BGP 120. R1 configure router neighbor 10.0.0.2 remote AS130. The following commands are used to change the IBGP. R1 config router BGP 120. R1 config router neighbor 192.168.1.20 remote AS120. As mentioned earlier, when exchanging routes within AS, IBGP doesn't modify the next hop field. This can become problematic because the next hop is the IP of the neighboring AS router, and unless it is redistributed by using an IGP, the internal network will reject the routes because the next hop is invalid. So the following command sets its own IP at the next hop route: R1 config router neighbor x.x.x.x next hop self. BGP also has a network command. This is used to specify a route that will be advertised in BGP. This route should exist in the routing table to be advertised in BGP. R1 config router network 10.20.20.0 mask 255.255.255.0. It is also possible to omit the mask command, doing which it takes the network as a classful one. There are a lot of other commands in BGP that Packet Tracer doesn't support, so we'll go ahead and configure a topology using these commands. For this exercise, we'll use a single multi-home design shown in the following screenshot, as Packet Tracer doesn't support IBGP. The following topology has 4 routers, 2 belonging to 2 different enterprises and the other 2 belonging to 2 different ISPs. Both the enterprise routers have loopback interfaces configured with the IP addresses shown in the topology. This is to demonstrate the injecting of routes into BGP. The following table lists the interfaces and their IP addresses. A device interface IP address subnet mask enterprise 1 loopback 0 20.30.0.1 255.255.0.0 fast ethernet 0/0 10.0.0.1 255.255.255.252 fast ethernet 1/0 10.0.0.9 255.255.255.252 enterprise loopback 040.30.0.1 255.255.0.0 fast ethernet 0/0 10.0.0.5 255.255.255.252 fast ethernet 1/0/10.0.0.13 255.255.255.252 ISP Fast Ethernet 0/4/010.0.0.2 255.255.255.252 Fast Ethernet 1/0 10.0.0.6 255.255.255.252 ISP2 Fast Ethernet 0/4/0 10.0.0.10//255.255.255.252 Fast Ethernet 1/4/0 10.0.0.14 255.255.255.252. The following are the steps to configure BGP on the meshed network topology. Let's start configuring BGP on the enterprise routers. Enterprise 1 config router BGP 10200. Enterprise 1 config router BGP router ID 0.0.0.1. Enterprise 1 config router neighbor 10.0.0.2. Remote AS 30200. Enterprise 1 config router neighbor 10.0.0.10. Remote as 50300. Enterprise 1 config router network at 20.30.0.0 mask 255.255.0.0. Enterprise 2 config router BGP 3400. Enterprise 2 config router BGP router ID 0.0.0.2. Enterprise 2 config router neighbor 10.0.0.6. remote as 30200. Enterprise 2 config router neighbor 10.0.0.14. remote as 50300. Enterprise 2 config router network 40.30.0.0 mask 255.255.0.0. Now let's configure ISP routers. ISP config router BGP 30200. ISP config router BGP router ID 1.1.1.1. ISP config router neighbor 10.0.0.1. remote as 10200. ISP config router neighbor 10.0.0.5. remote as 3400. ISP 2 config router BGP 50300. ISP 2 config router BGP router ID 2.2.2.2. ISP config router neighbor 10.0.0.9. remote as 10200. ISP2 config router neighbor 10.0.0.13. remote as 3403. You should now see console messages indicating that a BGP neighbor is up. %BGP 5ADJ change neighbor 10.0.0.9 up. %BGP 5ADJ change neighbor 10.0.0.13 up. For now, try pinging from enterprise to the loopback address of enterprise 2. Enterprise 1 ping 40.30.0.1. Type escape sequence sending 100 byte ICMP echoes to 40.30.0.1. timeout 2 seconds. Success rate is 0%. 0/5. We see that it fails. This is because the ICMP request packet uses a source address of 10 10.0.0.1. So when this packet is received by Enterprise 2, it doesn't have a route to 10.0.0.0/30 for sending a reply. We use the network command to inject only the routes of loopback addresses. Hence, we shall use the source address of the loopback itself using an extended ping. Enterprise 1 enable Enterprise 1 ping protocol IP target IP address 40.30.0.1 extended commands NY source address or interface loopback 0 type escape sequence to abort sending 100-byte ICMP echoes to 40.30.0.1 timeout is 2 seconds packet sent with a source address of 20.30.0.1 success rate is 100% 5/5 round trip MN average max equals 62 63 ms. So we have basically configured eBGP. Let's take a look at the routing table. If you look at the path column, you can see the ASNs that come in the path of the destination. The symbol indicates a preferred route. Summary: in this chapter, we learned the various designs used by organizations to connect to the internet. Then we saw the widely used routing protocol BGP, its features when compared to IGPs and its configuration. Sadly, Packet Tracer doesn't support IBGP, but if you can get your hands on real hardware or dynips, you can try it out. In the next chapter, we'll learn all about the latest game changer of networks, IPv6. We will start by learning how to assign IP addresses to it and then go about configuring routing. Finally, we'll learn how to use both IPv4 and IPv6 in a network. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.